So today what we're going to talk about, and in fact for the next 3 or 4 lectures, is using our new register building block, our new toy, to build all sorts of interesting systems. And in some ways the sort of rectangle and cloud schematic that you see sort of in cartoon form above the hack's head there, that's the hack and the nerd, but that's how I always think of them. So that's that cartoon is really a representative of pretty much all the circuits that we build in the digital world, which consists of storage elements which save state and computational elements that manipulate inputs and the current state to produce new states and outputs. And that's, that schematic diagram is sort of the key to all the digital circuits, and we're going to spend a little bit of time figuring out how to use it in an intelligent way. Before we dive into building finite state machines, which is our name for this sort of new abstraction that we're going to introduce, let me just remind you one last time about the timing involved in making register circuits work. So the canonical sort of setup is we have a register that's providing information to this combinational cloud, and then the result is captured in some downstream register. I've shown 2 registers here. If this guy looped back to the D input of the first register, everything would be exactly the same. The analysis would be the same. But basically we have a register sourcing information, combinational cloud, and a register syncing information. And this diagram down below is a fairly careful drafting of when signals are changing and when they're the same. So the clock edge, as you can see, is just in this case I've drawn a square wave. It's the rising edge of the clock, which is the so-called active edge. That's the one that loads new states into the registers. After the rising edge of the clock, it takes a certain amount of time for the output of the register to get contaminated. At least for a little while, it's maintaining the previous state value. After the contamination delay, you can't rely on the output of the register, so that's what that little hashed lozenge means. Gotta practice my words before I come down. And then finally, the output of the register becomes stable in its new state. So we're basically contamination delay, propagation delay. This funny symbol, this sort of graph here, indicates that the value is either 0 or 1. We're not being specific about whether it's 0 or 1, but we're indicating its periods of stability and when it changes. So when you see a clear lozenge, that's when it's stable. In other words, no changes happening there. And the hashing represents regions of time in which the signal may be changing. So that sort of sets up the timing for the values on the Q1 wire relative to the clock. We can then look at the output of the piece of combinational logic, which is also the input to the downstream register. And if we then take into account the contamination delay of the combinational logic, we can see that the star signal sticks around from the rising edge of the clock for the sum of the contamination delays of the upstream register and the contamination delay of the combinational logic cloud. In other words, this signal stays valid for a certain amount of time after the rising edge of the clock. It then starts to change and finally gets its new stable value after the sum of the propagation delays. It's this node down here, the star node, the input to the downstream register, where we have to then check that we meet the timing constraints imposed by the dynamic discipline. In other words, we have to meet the setup and hold times of the downstream register, and those are with respect to the rising edge of the clock, so that the downstream register will in fact work correctly. If we violate the setup and hold times, the downstream register isn't reliable, and in fact may do very funny things, and the very funny things are the subject of Thursday's comedy lecture, I guess. Okay, so this is a very careful diagram, and from this we'll get 2 timing constraints. And this is where you want to go borrow Professor Umbridge's pen. Remember the one that when you write, it inscribes in the back of your hand? This is a good thing to inscribe on the back of your hand. I mean, if you had to put down one set of timing equations, this would be the thing you should remember. And so while you're all cringing slightly, you can instead just say, how about if I just commit them to memory? And so the first constraint here, which is represented by this T1 interval, is the sum of the contamination delays. And that's how long the star signal remains valid after the rising edge of the clock. And we know that for the downstream register to work correctly, that the sum of the contamination delays has to be bigger than the hold time. Okay, so in rhythm, we all want to say the sum of the contamination delays has to be bigger than the hold time of the downstream register. So if we violate that constraint, the downstream register will not work correctly. So we have to somehow design our logic so that's true. The second timing constraint has to do with this T2 timing interval, which is sort of how long after the rising edge of the clock is it before we have a new stable value on the star signal, the one that will become loaded, that will be loaded into the downstream register on the rising edge of the next clock, on that rising edge. And the answer is, well, we're going to sum up all the propagation delays. The propagation delay of the register, that's here, okay, plus the propagation delay of the logic. That tells us how long it is before that star signal becomes stable with its new value, the one that reflects the new information coming out of the upstream register. At that point, the signal has to be valid for T setup. In other words, we have to meet the setup time of the downstream register. So what has to fit in between two clock edges? The propagation delay of the register, the propagation delay of the combinational logic, and the setup time that we need for this to work correctly. Okay. So these are the two timing constraints. They're not very hard to remember, particularly that we have umpteen practice problems for you to try it on, so I encourage you to do that. So how much time? So in some sense, the useful work is being performed by the combinational logic. How much time is there? Well, we take the clock period and we subtract off the propagation delay of the upstream register and the setup time of the downstream register. Those are properties inherent to the register, and we have to obey them, otherwise the registers don't work. Okay, I mean the downstream registers certainly needs its setup time, and the propagation time of the upstream register is just whatever the manufacturer sold you. So the clock period minus the prop time of the upstream register and the setup time of the downstream register, taken together, you subtract that from the clock period, and that's how much time you have in the middle to do actual work. This particular constraint down here, the sum of the contamination delays, might be handy if we actually design registers so that it was always true that their own internal contamination delay was greater than their hold time. That way, no matter if I, for instance, had no combinational logic and simply connected the wire, and you say, why would I do that? And you'll see when we do pipelining diagrams in the coming weeks that there will be times when we have so-called back-to-back registers. If we have this constraint here, if we actually design the register for this true, timing constraint 1 is actually met trivially. And then there are some issues about what happens when the clock signal doesn't actually get to all the registers at the same time. And that's called clock skew.